Look up at the night sky, and you'll spot Venus shining brilliantly, often called the evening star, our closest planetary neighbor and Earth's so-called twin. From a distance, it seems serene, almost welcoming, wrapped in dazzling clouds that reflect the sun's light. But behind that radiant glow lies one of the most hostile and mysterious worlds in our solar system. A place where the surface temperatures are hot enough to melt lead, where crushing atmospheric pressures would flatten any spacecraft within moments, and where thick clouds of sulfuric acid shroud the landscape in perpetual mystery. This is not the gentle sister planet we imagine. It's a world of extremes, of unanswered questions, and of secrets that have baffled scientists for decades. What makes Venus such an enigma? Why does a planet so similar to Earth in size and composition tell such a dramatically different story? From bizarre geological formations that defy explanation to atmospheric anomalies that challenge everything we know about planetary science, Venus holds puzzles that even our most advanced probes and telescopes have struggled to solve. Each mission to Venus has returned more questions than answers, pulling back the veil just enough to reveal how little we truly understand. This is a world where the ordinary rules of planetary behavior seem to break down, where the line between the possible and the inexplicable blurs with every new discovery. In this video, we're setting off on a journey to explore 25 of the most captivating and unresolved mysteries of Venus phenomena that continue to ignite curiosity and debate among astronomers, researchers, and space enthusiasts around the world. We'll venture into the strange, super-rotating atmosphere that whips around the planet faster than Venus itself rotates. Dive into the possibility of active volcanism on a world thought to be geologically dead, and examine the haunting signals that hint at lightning dancing through those toxic clouds. This isn't just a list of facts. It's an invitation to explore the frontiers of human knowledge, to stand at the edge of the unknown and wonder what lies beyond. So join us as we unravel the secrets of our mysterious sister planet and discover why Venus remains one of the greatest puzzles in our cosmic backyard. Think of Earth and Venus as siblings born from the same cosmic cloud of gas and dust. They're nearly identical in size and mass, composed of similar rocky materials, and they formed in the same neighborhood around the Sun. In many ways, they started out as twins, but while Earth evolved into a lush, watery world teeming with life, Venus became a hellscape, a stunning example of a climate catastrophe gone horribly wrong. So what happened? The leading theory points to a terrifying process known as a runaway greenhouse effect, and understanding it is crucial because it holds a warning for our own planet. The story likely begins with water. Scientists believe that early Venus might have been far more hospitable, possibly even boasting shallow oceans and a temperate climate. But being closer to the Sun, Venus received more solar energy. That extra heat began to evaporate its oceans, pumping vast amounts of water vapor, a potent greenhouse gas, into the atmosphere. This water vapor trapped more and more heat, which in turn evaporated even more water, creating a devastating positive feedback loop with no off switch. The planet's temperature began to skyrocket. This is where the true runaway began. The intense ultraviolet radiation from the Sun eventually hit the water vapor high in the atmosphere, breaking it apart into hydrogen and oxygen. The lightweight hydrogen, no longer bound in water molecules, simply escaped into space. This was the point of no return. Venus was losing the very element that could have moderated its climate. With its oceans gone forever, the stage was set for carbon dioxide to take over. The heat baked the carbon dioxide out of the rocks and surface, but with no oceans to absorb it and no plant life to sequester it, the gas built up in the atmosphere relentlessly. Today, the result is an atmosphere that is almost 96% carbon dioxide, a suffocating blanket that creates unimaginable surface conditions. The pressure at the surface is about 92 times that of Earth's, equivalent to being nearly 3,000 feet deep in Earth's ocean. This dense atmosphere acts like a supercharger for the greenhouse effect, trapping solar energy with terrifying efficiency and driving surface temperatures to a constant 870 degrees Fahrenheit, which is indeed hot enough to melt lead. This self-perpetuating cycle of heat and gas is the ultimate warning of what can happen when a planet's climate system spirals completely out of control. And this unimaginable heat leads us directly to one of the most visually striking and mechanically baffling mysteries of Venus: the super-rotation of its atmosphere. If you could stand on the scorching surface of Venus, you would experience a day that is longer than its year. The planet itself rotates backwards and with agonizing slowness, taking 243 Earth days to complete a single spin. But if you could somehow float high up in those thick, yellow clouds, you would be caught in a perpetual hurricane-force wind, screaming around the entire planet once every 4 Earth days. This means the upper atmosphere is racing around Venus 60 times faster than the planet's solid body is turning. It is a meteorological marvel unlike anything else we see in our solar system. We are familiar with weather systems being driven by a planet's rotation. On Earth, our spin creates global wind patterns like the jet stream. But on Venus, the atmosphere seems to be operating under a completely different set of rules, moving with a momentum that is largely divorced from the sluggish world below it. This creates a surreal and disorienting environment where the sky is perpetually in a frantic rush above a surface that is a L-M-O-S-T Chinese letter, Chinese letter, Chinese letter. Unraveling the engine behind this super-rotation is crucial because it challenges our fundamental understanding of how atmospheres and planetary bodies interact. So what force could possibly be pushing this immense blanket of gas to such incredible speeds? The leading theory points to a complex combination of solar heating and planetary scale waves. The sun's intense energy heats the atmosphere at the equator more than at the poles, creating a massive temperature difference. This thermal energy is then converted into kinetic energy motion. But on its own, that doesn't fully explain the sustained hurricane-like speed. Scientists believe atmospheric tidal waves, generated by the sun's gravitational pull on the thick air, may act as a constant pushing force, transferring energy and momentum into the atmosphere to keep it whipping around. Another fascinating component might be something called thermal tides. Unlike ocean tides caused by the moon's gravity, thermal tides are pressure waves in the atmosphere driven by the extreme heating of the sun on the planet's day side. This creates a massive bulge of hot, expanding atmosphere that travels across the planet, helping to drive the winds forward. It's a complex, planet-wide system where heat and motion are locked in a feedback loop that we are only beginning to comprehend. Each spacecraft mission, from the historic Pioneer Venus probes to the more recent Akatsuki orbiter, has sent back data that adds another piece to this puzzle. Yet a complete picture of the engine driving these winds remains one of Venus's most compelling secrets. And yet, even the planet's frantic, high-speed winds are only part of the atmospheric puzzle. To understand how Venus became the scorched world it is today, we must solve one of its most fundamental mysteries, the case of its missing water. This mystery is deeply intertwined with the runaway greenhouse effect we just explored, but it presents its own unique and haunting questions. The evidence is compelling that Venus was once a much wetter world, potentially even home to shallow oceans not unlike Earth's in its infancy. Today, however, the entire planet is almost completely desiccated. If you were to take all the trace water vapor left in its atmosphere and condense it into liquid, it would barely form a puddle across the planet's surface. The sheer scale of this loss is staggering, pointing to a planetary scale event of almost unimaginable proportions. So how does an entire ocean simply vanish? The primary suspect is a powerful and relentless process known as photodissociation, a word that simply means broken apart by light. Here's how scientists believe it unfolded. As the runaway greenhouse effect began to heat the planet, vast quantities of water evaporated from those hypothetical early oceans, filling the atmosphere with water vapor. This water vapor rose high into the upper atmosphere, where it was exposed to the full, unfiltered fury of the sun's ultraviolet radiation. These high-energy photons from the sun acted like tiny bullets, striking the water molecules and violently breaking their chemical bonds, splitting them into their component atoms, hydrogen and oxygen. This is where the story takes a tragic turn for Venus. Once freed, these atoms faced very different fates. The heavier oxygen atoms likely combined with other elements in the atmosphere or sank back down toward the surface, perhaps even rusting the rocks below. But the lightweight hydrogen atoms, now unbound, simply floated to the very top of the atmosphere. Venus's gravity, which is about 90% of Earth's, wasn't strong enough to hold onto these tiny, fast-moving atoms. One by one, they achieved escape velocity and were lost forever to the vacuum of space, blown away by the solar wind. This process created a one-way door out of the atmosphere. The water molecules were shattered, and the building blocks for making new ones were irrevocably lost. But photodissociation might not have acted alone. Some theories suggest a second culprit may have accelerated the water loss: a missing planetary magnetic field. Earth is protected by its strong magnetosphere, which acts as a shield, deflecting the solar wind and preventing it from stripping away our atmosphere. Venus, however, lacks a global magnetic field generated internally. Without this protective bubble, the full force of the solar wind would have battered the upper atmosphere, potentially sweeping those liberated hydrogen atoms away even more efficiently. This combination of a relentless external assault and an internal chemical breakdown could have been a devastating one-two punch that drained Venus of its water over hundreds of millions of years. The implications of this great drying are profound. Water is not just essential for life as we know it. It is a fundamental geological lubricant. It helps regulate a planet's temperature through its cycle of evaporation and precipitation. It is crucial for plate tectonics, the process that recycles carbon and regulates Earth's long-term climate. By losing its water, Venus lost its thermostat and its geological recycling system, locking in the extreme greenhouse conditions that define it today. The mystery of the missing water is therefore the key to understanding why Earth's twin evolved into such a terrifyingly different world, serving as a permanent cautionary tale written in the chemistry of its barren sky and bone-dry rocks. Yet as dramatic as the loss of its oceans was, the atmosphere of Venus holds another, more subtle secret, one that reveals itself not in what's missing, but in an unexplained dark presence. When we observe Venus not in visible light, but through the lens of an ultraviolet filter, its serene, featureless clouds transform. They become a canvas of striking contrasts, mottled with dark, blotchy patches and long, streaky patterns that slowly churn and evolve over time. These are not shadows or simple gaps in the cloud cover. They represent a profound scientific puzzle. Something within those clouds is actively and efficiently absorbing ultraviolet radiation from the sun. And despite decades of observation and analysis, we still do not know what that something is. This unknown substance, dubbed the ultraviolet absorber, behaves unlike any other identified component of the Venusian atmosphere. It appears concentrated in the topmost layer of the planet's sulfuric acid cloud deck, approximately 40 to 50 miles above the scorching surface. The patterns it creates are not static. They change shape and drift, carried by those super-rotating winds, suggesting this mysterious material is intimately mixed within the cloud particles themselves. Its ability to soak up such a specific band of solar energy plays a significant role in the planet's overall energy balance, influencing both the dynamics of the upper atmosphere and the distribution of heat. Identifying this absorber is therefore critical to building a complete model of how Venus's climate system functions. So what could this enigmatic substance be? Scientists have proposed a range of candidates, each intriguing yet ultimately unproven. The most straightforward hypothesis points toward various sulfur allotropes, different molecular forms of sulfur. Elemental sulfur could exist in forms like S3 and S4, chains and rings of sulfur atoms that are known to absorb UV light. These could be produced by the photochemical breakdown of sulfur dioxide and carbonyl sulfide, two gases known to be present in the atmosphere. Another potential culprit is ferric chloride, a compound of iron and chlorine, which also has the right absorption properties. These explanations are chemically plausible and fit within our understanding of Venus's hostile environment, but so far, no mission has returned definitive spectral data that confirms their presence in the required amounts and locations. The enduring failure to find a simple mineral or chemical answer has, perhaps inevitably, led to a more speculative but fascinating line of inquiry. Could the ultraviolet absorber be biological? This is not a claim of little green men, but a serious scientific consideration based on extreme life on Earth. The middle cloud deck of Venus, where this absorber is found, is arguably the most habitable zone on the planet. At an altitude of around 30 to 40 miles, the temperature and pressure are surprisingly Earth-like, hovering near 86 degrees Fahrenheit and 1 atmosphere of pressure. The clouds are composed of sulfuric acid droplets, which is undeniably harsh, but we know of extremophile bacteria on Earth that not only survive but thrive in highly acidic environments. The concept of aerial life is not even purely science fiction. Here on Earth, microorganisms have been found living high in our own atmosphere. The idea proposes that any potential Venusian microbes would have evolved a protective shell or exist within a protective gel to withstand the acidity. Crucially, they might possess a pigment, a form of protection against the intense UV radiation, that just so happens to absorb the very wavelengths we see as those dark patches. In this scenario, the most famous mystery of Venus's clouds could, theoretically, be a vast, planet-wide bacterial mat drifting in the skies. While this remains a highly speculative long-shot hypothesis, it is a testament to the depth of this mystery that such a radical idea remains on the table, a tantalizing possibility that continues to motivate astrobiologists and ensure that our sister planet holds onto its secrets just a little while longer. This brings us to the planet's most fundamental and fiery mystery. Is Venus volcanically active right now? The evidence pointing toward a world of fire and rock is overwhelming, yet the definitive proof of a live eruption has always remained just out of reach. Venus is, without a doubt, the most volcanic planet in our solar system. Its surface is a testament to a violent and extensive geological past, covered in vast plains of solidified basalt lava, enormous shield volcanoes that dwarf Everest, and bizarre pancake-like domes unique to this world. The sheer number of identified volcanic features runs into the many thousands, painting a picture of a planet whose history has been utterly dominated by magma welling up from its interior. The most compelling clue for recent activity comes from the startling youth of its surface. Unlike ancient worlds like Mercury or the Moon, whose faces are scarred by billions of years of craters, Venus's surface appears remarkably fresh. When scientists count impact craters, the cosmic clock by which we date planetary surfaces, they find a surprisingly low number, all distributed randomly and in a relatively pristine state. This pattern suggests that around 300 to 500 million years ago, a cataclysmic planetary resurfacing event likely occurred. In a geologically short span of time, massive volcanic outpourings are thought to have flooded the entire globe, burying the old, cratered terrain under a new layer of fresh rock and effectively hitting the reset button on the planet's surface age. The critical question is whether this was a one-time event or the most dramatic episode in an ongoing volcanic cycle that continues to this day. For decades, this remained a captivating geological whodunit, a case built on circumstantial evidence from topography and crater counts. But recently, the case for present-day activity has grown much stronger, moving from the theoretical into the realm of direct detection. The smoking gun comes not from seeing flowing lava, but from sniffing the volcanic gases in the atmosphere. Missions like the European Space Agency's Venus Express Orbiter have detected sharp, transient spikes in the concentration of sulfur dioxide, a gas that is a classic fingerprint of volcanic eruptions. On Earth, a sudden spike in SO2 is a sure sign that a volcano has just blown its top, pumping gas high into the sky. On Venus, these gases shouldn't linger for long. They are quickly broken down by solar radiation. So when scientists see these sudden increases, it strongly implies something down below is actively replenishing the supply right now. Further tantalizing hints have emerged from closer to the ground. Radar data from missions like NASA Magellan has identified specific volcanic structures that appear to have changed shape between imaging passes, suggesting possible new lava flows. Even more compelling, an analysis of data from the 1990s revealed that a volcanic vent near the giant volcano Mont Mons seemed to have significantly enlarged over a short period, a telltale sign of a recent eruption. Then, in 2023, a groundbreaking study re-examining Magellan radar data claimed to have found direct evidence of a volcanic eruption that occurred while the spacecraft was in orbit, an unmistakable change in a volcanic vent, and a new lava flow on the surface. This would be the closest thing to catching a volcano in the act, a monumental discovery if confirmed. Yet for all this mounting evidence, the ultimate confirmation remains elusive. No spacecraft has yet been equipped with the right instruments at the right time and in the right orbit to directly witness an eruption in progress. We have not seen the incandescent glow of fresh lava in the darkness of the Venusian night, or imaged a plume of ash and gas rising into those yellow clouds. This leaves planetary scientists in a state of exciting suspense. The body of evidence is pointing overwhelmingly toward a geologically alive world, but the final piece of the puzzle is still missing. Understanding whether Venus is active today is about more than just checking a box. It is the key to unlocking the inner workings of this alien world, how it loses its internal heat, the nature of its tectonic processes, and why it took such a dramatically different evolutionary path from its twin, Earth. The hunt for an erupting volcano on Venus remains one of the most urgent and thrilling quests in planetary science. Now, if the global resurfacing event essentially erased Venus's earliest history, where can we look for clues about its distant past? The answer lies in a set of incredibly strange and ancient geological features that stand out like weathered, complex islands in a sea of younger volcanic plains. These are the tesserae, a term derived from the Greek word for tiles, and they represent the single most puzzling landscape on the entire planet. Imagine a vast, chaotic region of intensely deformed rock, crisscrossed by ridges and grooves that intersect in multiple directions, forming a pattern that looks like a cracked and crumpled mosaic. These terrains are not gentle rolling hills. They are heavily textured, rugged highlands that rise high above the surrounding flatlands, and they are believed to be the oldest surviving pieces of crust on Venus, dating back to a time before the Great Resurfacing event buried the rest of the ancient world. The formation of these tesserae terrains is a first-order geological mystery because they don't resemble anything we see on Earth in a simple, one-to-one way. Their complex, crisscrossing patterns of ridges and troughs tell a story of the crust being pushed, pulled, and sheared by immense tectonic forces from multiple directions, and not just once, but repeatedly over a long period. This creates a narrative of extreme and protracted deformation, a battle of forces that played out on the crust of Venus for eons. Unlocking how they formed is like finding a page from the planet's earliest diary, a record of the conditions and processes that shaped the young Venus, potentially offering a glimpse into why its geological evolution diverged so dramatically from Earth's. So what tectonic processes could create such bizarre and intricate landscapes? Planetary geologists have proposed several compelling models, each with its own merits and challenges. One leading hypothesis suggests that the tesserae are the result of large-scale crustal shortening. Imagine the planet's crust being slowly compressed from the sides, forcing it to buckle, fold, and break, piling up into these high, complex regions. The intersecting patterns could be explained if the direction of this compression changed over time, creating one set of folds and then another set on top of them, like wrinkles in a rug that spins scrunched from different angles. Another fascinating theory points to a process known as block rotation and strike-slip faulting. In this scenario, vast blocks of the ancient crust were jostled and shoved against each other by underlying mantle currents, similar to the way tectonic plates move on Earth, but without the clear, organized boundaries. As these blocks grinded past one another, their edges crumpled and fractured, creating the intersecting ridges and valleys we see today. A third, more exotic idea involves the potential for large-scale gravitational collapse of the crust. If parts of the early Venusian crust were built up very thick from massive volcanic activity, they might have become too heavy and unstable, eventually spreading out and collapsing under their own weight, creating the intensely deformed textures of the tesserae in the process. The true answer might even be a combination of these processes, or something entirely unique to Venus's peculiar environment. The planet's incredibly high surface temperature makes the crust behave more like a soft, warm plastic than the brittle rock we're familiar with on Earth, which could allow for a style of deformation for which we have no direct analog. This means the tesserae aren't just a puzzle. They are a window into a fundamentally different mode of planetary tectonics, one that operated under hellish conditions of heat and pressure we can scarcely replicate. Understanding them is crucial because they might hold the ultimate secret to Venus's early climate. Some models even suggest these high-standing ancient lands could have been the last refuges for any surface water, the final islands in a disappearing ocean, making them the most promising and most challenging places to search for clues that Venus was once a world not so unlike our own. Moving from the ancient, crumpled highlands of the tesserae, we now turn our gaze upward to a mystery that is not etched in rock, but painted in faint, ethereal light, a phenomenon that has captivated and confounded astronomers for hundreds of years. It's known as the ashen light, a soft, ghostly illumination reportedly seen on the dark side of Venus, the side shrouded in the profound blackness of its own night. Imagine a world where the sun is completely blocked, where no sunlight should reach the surface, and yet observers with powerful telescopes have occasionally witnessed a faint, eerie glow, like the embers of a dying fire scattered across the landscape of a world that should be utterly dark. The history of this mystery is as rich as it is puzzling. The first documented sighting dates all the way back to 1643, by the renowned astronomer Giovanni Riccioli. Since then, some of the most famous names in astronomy, including Sir William Herschel and Patrick Moore, have recorded their own observations of this faint luminescence. These are not novice stargazers. These are seasoned professionals with a deep understanding of the sky. Yet the phenomenon remains maddeningly elusive. It does not appear on command. It is not something every observer can see every time they look. It flickers into view for some and remains completely invisible to others, even when using the same equipment on the same night. This inconsistency is a core part of the mystery, making it nearly impossible to study systematically and leading many to question whether it is a real physical event or a trick of the eye, an optical illusion born of extreme contrast. But if we assume that at least some of these dedicated astronomers truly saw something, then we are left with a fascinating scientific puzzle. What could possibly be generating light on the eternal night side of Venus? The planet has no large moon to act as a reflector, like our own moon lights up Earth's night. So the source of this glow must be internal, something happening within the planet's atmosphere or on its surface. The leading theories are as varied as they are intriguing, each attempting to explain this elusive flicker in the dark. One compelling explanation points to intense electrical activity in the Venusian atmosphere, specifically lightning. On Earth, a powerful lightning storm can illuminate the clouds from within, creating a diffuse glow that can be seen from hundreds of miles away. If Venus has frequent and widespread lightning discharges within its thick, turbulent cloud layers, that could theoretically provide the necessary light. The problem is that while some missions have detected signals suggestive of lightning, it has never been visually confirmed, and it's unclear if it would be widespread or energetic enough to create a globe-spanning glow visible from Earth. The light from lightning would also be fleeting and flashy, not the steady, soft glow that many reports describe. Another strong candidate involves a phenomenon we see at Earth's poles, auroras. Here, charged particles from the solar wind are funneled by our magnetic field toward the poles, where they collide with atoms in the upper atmosphere, making them glow. Venus lacks a global magnetic field to guide these particles, but the solar wind does interact directly with its upper atmosphere, potentially creating a weak, planet-wide aurora that could be the source of the ashen light. This would be a very different kind of aurora than Earth's dazzling displays, perhaps a much fainter and more uniform veil of light, which aligns well with the descriptions from observers. A more recent and technologically sophisticated theory involves a process called airglow. This is a faint emission of light that occurs when atoms and molecules in the upper atmosphere, excited by the sun's ultraviolet radiation during the day, release that energy as light after the sun has set. This is a well-documented phenomenon on Earth, and it's something the Venus Express orbiter actually detected. The spacecraft measured a green glow emanating from oxygen atoms high in the Venusian atmosphere on the night side. While this detected glow was extremely faint, perhaps too faint to be seen from Earth-based telescopes, it proves that such chemical light production is actively occurring, providing a tangible, if not yet definitive, piece of the puzzle. Yet for every theory, there is a counterargument. The airglow detected by spacecraft is likely too weak. Auroras on a planet without a magnetic field are poorly understood. Lightning remains unproven. This has led to even more exotic suggestions, such as the possibility of volcanism. If Venus is indeed volcanically active, the incandescent glow of fresh, red-hot lava flows in the darkness could provide localized points of light. If a large enough eruption were occurring on the night side, it could theoretically be glimpsed from Earth. While this seems like a long shot, it connects this atmospheric mystery directly back to the planet's fiery geological heart. The enduring enigma of the ashen light is a perfect example of a scientific frontier where human observation and modern technology have yet to converge on an answer. It is a whisper from the past, a puzzle noted in ink on parchment centuries ago, that continues to challenge our understanding of planetary physics today. It reminds us that sometimes the most persistent mysteries are not those hidden in the data of satellites, but those glimpsed fleetingly through the eyepiece, urging us to keep looking, to keep wondering what secrets the darkened face of our sister planet might still be holding. And just as we grapple with these fleeting glimpses of light, another far more concrete signal from Venus's clouds recently ignited a firestorm of debate, one that reached beyond the astronomy community and captured the world's imagination. This was the explosive phosphine controversy of 2020, a modern scientific detective story that began with a startling claim and unfolded into a fierce, ongoing debate about what, or who, might be creating a peculiar gas in the planet's atmosphere. It started with a team of astronomers using two of the most powerful radio telescopes on Earth, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. They weren't looking for life. They were conducting a rigorous survey of Venus's atmosphere, searching for any unusual chemical compounds. Their focus landed on a very specific wavelength of light that is absorbed by a simple molecule, phosphine, which is made of one phosphorus atom and 3 hydrogen atoms. To their astonishment, the data showed a clear absorption line at that exact wavelength, a signature that pointed to a small but significant amount of phosphine gas present in the planet's temperate cloud deck. The concentration was about 20 parts per billion, not much, but undeniably there according to their analysis. The reason this simple discovery caused such an uproar is because of what phosphine represents here on Earth. On our planet, phosphine is a gas that is famously and almost exclusively associated with life. It's produced industrially by humans, but in nature, it's only known to be manufactured by certain kinds of anaerobic bacteria, microbes that thrive in oxygen-free environments like swamps, marshes, and the guts of animals. Crucially, it's incredibly difficult to make phosphine through any known non-biological, geological, or chemical processes under the conditions found on a rocky planet. The amount of energy required is immense, and the natural chemical pathways we know about simply don't produce it in the quantities the team claimed to detect. So, the breathtaking implication was that if this detection was real, and the gas was indeed phosphine, and if all known non-biological sources could be ruled out, then the most extraordinary explanation remaining was that some form of microbial life was floating in the clouds of Venus, producing this gas as a byproduct of its metabolism. The announcement was met with a tidal wave of excitement, skepticism, and intense scrutiny from the broader scientific community. Other teams of researchers immediately began to reanalyze the same data. Some groups suggested that the original team might have misidentified the signal, arguing that what was interpreted as phosphine could actually be a much more common gas, sulfur dioxide, which absorbs light at a very nearby wavelength. The plot thickened as the original team reworked their analysis, acknowledging that the signal was weaker than first thought, but still, in their view, present. The debate raged back and forth in prestigious journals, a public and passionate display of how science self-corrects. It became a classic example of extraordinary claims requiring extraordinary evidence, with every step of the process from the data processing to the statistical analysis being picked apart in minute detail. This rigorous challenge forced everyone to think more creatively about Venus itself. If it wasn't life, what unknown chemistry or geology on this alien world could be manufacturing phosphine? Scientists scrambled to propose alternative mechanisms. Could micrometeorites depositing phosphorus-rich dust into the atmosphere trigger a reaction? Might powerful volcanic eruptions spew phosphides from deep within the planet up into the clouds, where they could then react with the sulfuric acid to form phosphine? Could lightning strikes or some other form of exotic atmospheric chemistry, completely novel to us, be at work? Each idea was fascinating but faced its own hurdles, unable to easily account for the proposed amount of gas or the specific conditions in the Venusian cloud layers. The phosphine saga is far from over. New observations are planned, and future missions like NASA Da Vinci and the European Envision orbiter will carry instruments specifically designed to settle the matter. What began as a single, tantalizing data point has evolved into one of the most compelling mysteries of our time. It forced us to look at our sister planet not just as a geological wonder, but as a potential biological frontier. It challenged our assumptions about where life could exist, and pushed scientists to discover new fundamental chemistry. Whether the final verdict confirms a biological source or reveals a previously unknown abiotic process, the phosphine controversy has already irrevocably changed our relationship with Venus, transforming it from a cautionary tale of a dead world into a prime target in the search for life elsewhere in the universe. This profound difference in magnetic shielding leads us directly to another of Venus's most fundamental mysteries, one that lies hidden deep within its core. We've seen how Earth's churning, molten iron heart generates a powerful protective magnetic field. Venus, our planetary twin, is nearly identical in size and composition to Earth. It almost certainly also possesses a molten iron core, much like our own. And yet, despite this seemingly identical setup, Venus has no planet-wide magnetic field to speak of. It's as if one twin was born with a powerful immune system, while the other was left completely vulnerable. And understanding why gets to the very heart of planetary evolution. The absence of this protective shield is not a minor detail. It's a defining feature that has shaped Venus's entire history. Without a magnetic bubble to deflect it, the full force of the solar wind, a constant, supersonic stream of charged particles blasting from the sun, slams directly into the planet's upper atmosphere. This relentless assault has likely played a significant role over billions of years in stripping away Venus's water, as those lightweight hydrogen atoms, freed from broken water molecules, were easily picked off and swept out into space. The solar wind continues to erode the outer layers of the atmosphere even today, a slow but steady leak that would be drastically reduced if a magnetic field were present. So why would two planets, forged from the same materials in the same cosmic neighborhood, end up with such dramatically different internal engines? The prevailing theory points to a critical difference not in the core itself, but in the churning motion above it. Earth's magnetic field is generated by a self-sustaining dynamo. Our planet's rapid rotation acts like a giant crank, driving the convection of the molten iron in the outer core. This combination of heat-driven convection and the planet's spin creates complex spiraling currents, and the movement of this electrically conductive fluid generates the magnetic field. It's a sophisticated planetary engine that requires several key ingredients to work: a liquid, conductive core, a source of heat to drive convection, and crucially, a sufficiently fast rotation to organize that convection into a coherent global field. This is where Venus appears to fall short in a dramatic fashion. A single day on Venus lasts 243 Earth days. Its rotation is not only incredibly slow, but it's also backwards, or retrograde. This lack of spin is the leading suspect for why its dynamo is dead. The thinking is that without a rapid rotation to get the molten iron churning in an organized, spiraling pattern, the convection in Venus's core becomes chaotic and disorganized. Heat still rises from the core and cools near the mantle boundary, but this motion may be more of a sluggish, roiling turmoil than the structured, spiraling flow needed to generate a powerful magnetic field. It's the difference between stirring a cup of tea with a smooth, circular motion and just jiggling the cup randomly. Only one method creates a coherent swirl. However, the story might be more complex than just a lack of spin. Some planetary scientists propose that the stifling conditions on the surface are a clue to what's happening deep below. Venus's incredibly thick, crushing atmosphere and searing surface temperature might prevent the planet from cooling down efficiently. On Earth, our dynamic plate tectonics act like a planetary cooling system. The continuous recycling of the crust allows heat from the interior to escape effectively. Venus, with its stagnant lid tectonic style, a single, unbroken plate may be effectively insulated, trapping its internal heat. Without a significant temperature difference between the core and the mantle, the driving force for the vigorous convection needed to power a dynamo could be weakened. The core might even be in a state of what's called thermal stratification, where it's too warm to create the strong convective plumes necessary for a magnetic field, leaving the liquid iron largely still and unable to generate a global dynamo effect. The mystery is further deepened by the discovery of a very weak, induced magnetosphere. While Venus lacks an intrinsic magnetic field generated from within its core, the interaction of the solar wind with the planet's ionosphere, a layer of charged particles in its upper atmosphere, creates a faint external magnetic barrier. This field is weak, wobbly, and entirely dependent on the pressure of the solar wind, offering only a fraction of the protection that Earth's powerful intrinsic field provides. Studying this induced field helps scientists understand the complex physics of solar-wind interaction, but it does little to solve the deeper puzzle of the silent core. Unraveling why Venus's dynamo failed is about more than just solving a planetary anomaly. It is a key to understanding the very conditions necessary for a world to protect itself and preserve the elements that could make it habitable. The answer lies locked within that silent, molten sphere of iron, waiting for a future mission to finally listen. While our modern orbiters and telescopes gather data from afar, some of the most tantalizing clues about Venus come from the few times humanity has actually touched its surface. In the 1970s and 80s, the Soviet Union achieved what remains one of the most incredible feats of space exploration. They successfully landed a series of probes on the hellish surface of Venus. The Venera landers were engineering marvels, designed to survive for mere minutes in an environment that was essentially a supercritical pressure cooker filled with acid. They transmitted back the first, and still the only glimpses we have from the surface of another planet, grainy black and white images that revealed a rocky, desolate world under an orange-hued sky. But along with these triumphant firsts, the Venera missions also returned a handful of peculiar data points and images that have fueled speculation and debate for decades. Small anomalies that hint at processes we still don't fully understand. Perhaps the most famous of these mysteries comes from the Venera 13 and 14 landers, which touched down just days and about 950 kilometers apart in March of 1982. Both were equipped with sophisticated soil samplers, designed to drill into the Venusian rock, collect a sample, and bring it inside the lander to an airtight chamber for X-ray fluorescence analysis. This was a precise experiment to finally determine the elemental composition of the Venusian surface. The results were clear, but for one of the landers, they were also completely unexpected. The two sites, while geographically separate, were expected to show broadly similar geology, yet the readings were dramatically different. Venera 14's analysis showed a composition very similar to toleiitic basalt, a common volcanic rock found on Earth, Mars, and the Moon. It was exactly what scientists anticipated. Venera 13's results, however, were anything but normal. Its instrument detected a rock of a type called alkaline potassium-rich trachyte. This is a much more evolved and rarer volcanic rock, one that implies a complex and protracted geological history of fractional crystallization within a magma chamber. On Earth, such rocks are associated with very specific and unusual volcanic systems. For them to be present on Venus suggests a far more geologically complex past than the simple global outpourings of basalt that the resurfacing theory suggests. The profound mystery is why two landers, so relatively close together on a global scale, would sample such fundamentally different crustal material. It implies a shocking lack of uniformity in the young lava plains, pointing to a volcanic diversity on Venus that we are only beginning to appreciate, and one that we have not had the chance to explore since. But the physical anomalies don't stop with chemistry. The landers also returned a series of photographs, and within a few of these grainy, panoramic images, some researchers believe they see evidence of something even stranger. The most discussed example is a small object near the Venera 13 lander that some have informally dubbed the Scorpion due to its vague, articulated shape. It appears in one image of a sequence, but is absent from a subsequent image taken minutes later from a slightly different angle. Proponents of it being a real surface feature suggest it might have moved, perhaps blown by the wind or even, in the most extreme speculation, possessing a means of independent motion. Mainstream planetary scientists overwhelmingly attribute this and other objects to known image processing artifacts. The Venera images were transmitted via analog slow-scan television and were painstakingly reconstructed on Earth, a process that could introduce noise, compression artifacts, or lens flare that the human brain, ever eager to find patterns, interprets as a familiar shape. It is a classic case of pareidolia, like seeing a face in the clouds. However, dismissing every anomaly as mere noise might be too simplistic. Other curious features have been noted, such as a hinged-looking, circular object near Venera 9 that bears an uncanny resemblance to the lander's own camera lens cap, which was jettisoned upon landing. The problem is that the lens cap was ejected in the opposite direction. This has led to endless debate. Is it just a strangely shaped rock that happens to look manufactured? Is it a piece of the lander that broke off in a way not accounted for in the mission logs? Or does it point to something else entirely? These discussions highlight the fundamental challenge of the Venera data. We have a tiny handful of data points from a handful of locations on an entire world, captured with 1970s technology under the most extreme duress. Isolating a true signal from the noise is incredibly difficult, and the inability to return for a closer look has forever sealed these mysteries in amber. The true legacy of these Venera anomalies is not that they provide proof of the extraordinary, but that they underscore how little we truly know about the Venusian surface. The divergent soil samples suggest a world with a rich and varied geological history that we have only barely glimpsed. The ambiguous objects in the photographs, whether mere artifacts or not, remind us that the surface of Venus is an environment beyond our everyday comprehension, where processes and materials might create forms that seem alien to our eyes. They are a testament to the audacity of those early missions and a powerful reminder of why we must go back. Only with modern sensors, longer-lived landers, and rovers can we hope to distinguish between a photographic glitch from 1982 and a genuine discovery waiting on the dusty, wind-swept plains of our sister planet. While the super-rotating winds create a planet-wide hurricane in the upper atmosphere, a more recent and localized discovery has added another layer of complexity to Venus's meteorological madness. High above the equator, embedded within those already frantic winds, scientists have identified a surprisingly narrow and incredibly fast-moving river of air, a jet stream screaming through the Venusian sky. This isn't just a slightly faster breeze. It's a concentrated atmospheric torrent that challenges the very foundation of our models for how air circulates on a planet like Venus, presenting a puzzle within a puzzle that researchers are scrambling to solve. The discovery of this equatorial jet is a testament to the power of dedicated observation. It was Japan's Akatsuki orbiter, which arrived at Venus in 2015, that provided the clear and persistent data needed to spot this feature. By carefully tracking the movement of the planet's distinctive cloud features over time, the spacecraft's cameras were able to map wind speeds at different altitudes with unprecedented precision. What they found was astonishing. A narrow band of atmosphere, roughly 10 degrees north and south of the equator, where the wind velocity suddenly spikes. The winds here were measured racing at over 80 meters per second. That's about 180 miles per hour, significantly faster than the already impressive super-rotating winds surrounding it. This jet isn't a constant, stable feature either. It appears to wax and wane in strength, sometimes even seeming to double in its intensity before calming down again, adding a dynamic and unpredictable element to the atmospheric choreography. This finding is so perplexing because it defies the standard expectations for atmospheric behavior on a slowly rotating planet. On Earth, our powerful jet streams are largely the product of two major forces: the temperature difference between the poles and the equator, and perhaps more importantly, the planet's rapid rotation. The Coriolis effect, caused by Earth's spin, helps organize these temperature-driven air movements into the concentrated bands of fast wind we know as jet streams. Venus, with its snail-like rotation that takes 243 Earth days to complete a single turn, has an extremely weak Coriolis effect. According to conventional atmospheric models, this weakness should prevent the formation of such a sharp, well-defined, and powerful jet stream. Its very existence implies that an entirely different, and currently unknown, set of forces must be at work, dominating the atmospheric physics there. So what could be powering this mysterious atmospheric river? Planetary scientists are investigating several compelling leads, each pointing to a complex interplay of forces unique to Venus. One primary suspect is a phenomenon tied to the planet's monstrous surface heat. The incredible temperature at the ground, hot enough to melt lead, creates massive thermal tides. These are planetary-scale waves of pressure that travel through the atmosphere, pushed by the immense heating from the sun on the day side. It's possible that the interaction of these thermal tides with the background super-rotation could be funneling energy and momentum into a specific atmospheric layer right at the equator, effectively squeezing the winds into this accelerated, narrow channel. Another theory looks to the planet's topography. While Venus's surface is mostly flat plains, it does have two major highland continents, Ishtar Terra and Aphrodite Terra. Some models suggest that as the super-rotating winds slam into these massive highland regions, they could generate enormous atmospheric waves that propagate upward, eventually breaking like ocean waves on a shore and transferring their energy to help form and sustain the jet. The equatorial jet is more than just an academic curiosity. It's a critical piece of the larger puzzle of Venus's climate system. Its behavior likely has a direct influence on how heat and chemical components are distributed across the planet. Understanding its driving mechanisms is essential for creating a complete and accurate global circulation model for Venus. Every time we think we have a handle on the dynamics of its atmosphere, a discovery like this jet stream emerges to remind us just how much we have yet to learn. It serves as a humbling and exciting reminder that even within a system as broadly strange as Venus's superrotation, there are finer, more intricate mysteries waiting to be unraveled, each holding a key to the complex and alien meteorology of our sister planet. But even the planet's dramatic jet streams are not its most visually arresting atmospheric feature. When viewed in ultraviolet light, Venus reveals its grandest and most enigmatic spectacle, a colossal, dark, Y-shaped pattern that seems to be permanently etched across its cloud tops, spanning the entire globe from the northern hemisphere down through the equator and into the south. This isn't a temporary storm or a fleeting atmospheric ripple. It's a persistent, planet-scale structure that has been observed for decades, a fixed shape somehow maintaining its integrity while being carried along by the hurricane force, super-rotating winds that circumnavigate Venus every 4 Earth days. The sheer scale and stability of this feature are baffling, presenting a paradox that challenges our understanding of fluid dynamics on a planetary level. The mystery of the giant Y is rooted in this apparent contradiction. The clouds themselves are composed of droplets of sulfuric acid and other aerosols, whipped around the planet at speeds exceeding 200 miles per hour. In any typical fluid system, you would expect such a massive, coherent structure to be quickly sheared apart, its distinct shape dissolving into the chaotic flow around it. Think of trying to preserve a perfect smiley face drawn in the foam on top of a rushing river. The current would distort and destroy the image almost instantly. Yet on Venus, this global Y pattern does the impossible. It holds its form for weeks or even months at a time, a stark, dark signature against the brighter clouds, all while racing around the planet. It's as if the atmosphere itself is imprinted with a ghostly, unchanging brand that rotates in lockstep with the winds. And planetary scientists have been working for over half a century to figure out what kind of atmospheric process could possibly create such a stable yet mobile phenomenon. The leading theory that has emerged to explain this persistent pattern involves a complex and fascinating interplay between the atmosphere's motion and the planet's slow, relentless rotation. It is thought to be a visible manifestation of a planetary-scale Kelvin wave. Unlike the waves we see on an ocean, which are traveling disturbances on the surface of the water, an atmospheric Kelvin wave is a type of trapped wave that propagates around the equator, balancing the Coriolis effect against the gravitational restoring force of the atmosphere's density layers. On a rapidly rotating planet like Earth, these waves are common, but don't usually create such dominant, fixed patterns. On Venus, with its weak Coriolis effect due to its incredibly slow spin, the conditions might be just right for a single, massive Kelvin wave to become the dominant feature of the entire atmospheric circulation, literally shaping the way the clouds themselves are distributed across the globe. This theory suggests that the wave is not just riding on top of the atmosphere, but is actually driving it. The dark regions of the Y are believed to be areas where the wave's dynamics are causing the cloud deck to dip slightly lower. In these slightly deeper atmospheric layers, the concentration of the mysterious ultraviolet absorber is higher, making those regions appear much darker to our instruments. The wave itself acts as an organizing force, gathering and concentrating these dark particles into its specific, Y-shaped path. The energy that sustains this massive wave is likely drawn from two primary sources: the intense solar heating at the planet's equator, which creates massive temperature differences, and the slow rotation of Venus itself, which provides just enough of a Coriolis force to trap the wave along the equator. It's a perfect, self-reinforcing feedback loop between the planet's spin, its absorption of solar energy, and the chemistry of its clouds, resulting in an atmospheric phenomenon of stunning grandeur and stability. But the story doesn't end there. Recent observations from the Japanese Akatsuki orbiter have added a new layer of intrigue to this already complex mystery. The spacecraft's sophisticated imaging has revealed that the Y-shaped pattern is not always a perfect, static structure. At times, it appears to break down and then reform, or it develops kinks and distortions that propagate along its length. This suggests that the interaction between the underlying Kelvin wave and the turbulent super-rotating winds is even more complex than previously imagined. Other types of atmospheric waves, generated by flow over surface features like mountains or by massive weather systems, might sometimes interfere with the primary Kelvin wave, causing these temporary disruptions. This means the giant Y is not just a simple wave pattern. It is likely the visible outcome of a constant, planet-wide battle between different atmospheric forces, a standing wave that must constantly assert itself against the chaotic background turbulence of Venus's insane weather. Unlocking the full secret of this giant, swirling signature in the clouds is therefore about more than just explaining a pretty picture. It is a critical step toward building a complete model of how energy and momentum are transferred across the entire Venusian atmosphere, a dynamic and beautiful puzzle written in the toxic haze of our sister planet. Given its status as Earth's twin, we might expect Venus to have an atmosphere of similar composition and density to our own, a mix of nitrogen and oxygen with just a trace of carbon dioxide. Instead, we find a crushing shroud of gas that is 96% carbon dioxide, with a surface pressure 92 times greater than Earth's. This leads to one of the most fundamental questions in planetary science. How did Venus acquire such an overwhelmingly dense and toxic atmosphere? And why did its evolutionary path veer so catastrophically from that of its sister planet? The answer appears to lie in a devastating combination of geology and chemistry, a story of carbon that was released but never reclaimed. The primary source of any rocky planet's atmosphere is a process known as outgassing. During a planet's fiery formation and its subsequent volcanic youth, immense quantities of gases trapped within the molten rock are released through eruptions, seepage, and direct venting into the air. For both Earth and Venus, the dominant gas released from their similar mantles would have been carbon dioxide, along with water vapor, nitrogen, and sulfur compounds. On both worlds, the early atmospheres were likely thick, hot, and dominated by carbon dioxide. This is where their stories begin to diverge in a profound and irreversible way. On Earth, a crucial planetary-scale recycling system emerged to manage this carbon, a process that Venus seemingly never developed. This is the critical role of plate tectonics. On our planet, The surface is broken into a mosaic of giant plates that slowly drift, collide, and most importantly, subduct. When an oceanic plate slides beneath a continental plate, it doesn't just recycle rock. It also pulls carbon-rich seabed sediments and even the carbon dioxide dissolved in seawater down into the hot mantle. This subduction acts as a planetary thermostat. The carbon is eventually released back into the atmosphere through volcanoes, but over millions of years, creating a long-term cycle that regulates the amount of carbon dioxide in the air. Furthermore, Earth's vast oceans act as a massive carbon sink, absorbing enormous quantities of the gas, which then becomes locked away in carbonate rocks like limestone. Life itself joined in, with marine organisms using dissolved carbon to build their shells, which then sank to the ocean floor to be buried and become part of the geological record. Venus, however, operates under what is known as a stagnant lid tectonic regime. Its crust is a single, unbroken plate, a rigid shell that seals the planet's interior. While there is evidence of vast volcanic plains and tectonic wrinkling, there is no continuous, large-scale recycling of the surface. This means the planet's carbon cycle is fundamentally broken. Volcanism in the distant past would have unleashed unimaginable quantities of carbon dioxide into the atmosphere through massive, global outgassing events. But without plate tectonics to pull that carbon back down into the mantle, the gas had nowhere to go. It simply accumulated in the atmosphere, building up over billions of years into the suffocating blanket we see today. The carbon was released in a one-way eruption from the planet's interior, with no mechanism to put it back. This geological failure was then catastrophically compounded by the loss of Venus's water. On Earth, our oceans are the other half of the carbon regulation system. Even if plate tectonics slowed, the oceans would continue to absorb carbon dioxide for a time. But as we explored earlier, Venus's water was brutally stripped away by a runaway greenhouse effect, itself likely triggered by that initial thick atmosphere and intense solar heating. With no oceans to absorb the carbon dioxide and no biological life to sequester it, the gas was left to rule the atmosphere absolutely. The very heat baked out even more carbon from the surface rocks, creating a terrifying positive feedback loop. More CO2 led to more heat, and more heat led to more CO2 being released, until the planet reached its current state of torrid equilibrium. The origin of Venus's atmosphere is therefore a tragic tale of two absences: the absence of a geological recycling system and the absence of a hydrological system, leaving the planet drowning in the elemental breath of its own fiery interior. Yet within that same thick and turbulent atmosphere, another form of powerful energy may be at play, one that sparks both scientific debate and a sense of awe: the enduring mystery of lightning on Venus. The concept is both terrifying and mesmerizing, the thought of brilliant electrical flashes illuminating the perpetual yellow gloom from within. A silent light show raging inside a global cloud of sulfuric acid. For decades, evidence for this phenomenon has been tantalizing, controversial, and incredibly difficult to confirm, creating a puzzle that challenges our understanding of how electrical discharges work on a world utterly unlike our own. The case for Venusian lightning began with our first visitors to the planet. Several of the Soviet Venera landers, as they descended through the oppressive atmosphere, detected low-frequency radio waves that strongly resembled the static bursts generated by distant lightning strikes on Earth. Then, NASA Pioneer Venus Orbiter, which studied the planet throughout the 1980s, also picked up similar electromagnetic Whistler waves, a specific type of very low-frequency signal that, on Earth, is unequivocally caused by lightning. These detections were compelling enough that for a long time, many scientists considered the existence of lightning on Venus to be a settled fact, a dramatic feature of its alien weather. The supposed mechanism was analogous to Earth: powerful updrafts and downdrafts within the thick clouds causing ice crystals and other particles to collide. building up massive separations of electrical charge that would eventually discharge as a lightning bolt. But the more we learned about the Venusian environment, the shakier this Earth-centric explanation became. The problem lies in the clouds themselves. On Earth, lightning is born in clouds of water ice, where collisions between ice crystals and supercooled water droplets are efficient at generating the charge separation needed for a spark. The clouds of Venus, however, are primarily composed of droplets of sulfuric acid, not water. This is a critical difference. Sulfuric acid is a much more efficient electrical conductor than water ice. In such a conductive environment, it is incredibly difficult for the large charge imbalances necessary for lightning to build up in the first place. The charge would likely simply leak away through the acidic droplets before it could ever accumulate enough to create a bolt. This fundamental physics problem has led many researchers to question whether the signals detected by the Venera and Pioneer missions were truly from lightning, or if they were caused by some other, unknown electrical phenomenon unique to Venus. This controversy was sharply reignited by the arrival of the European Space Agency's Venus Express orbiter in 2006. The spacecraft was equipped with a sophisticated magnetometer, an instrument perfectly suited to definitively search for the magnetic signatures of lightning. After years of meticulous observation, the results were startling. The orbiter failed to detect the high-frequency radio bursts that are the undeniable fingerprint of lightning. It observed plenty of low-frequency waves, but the crucial high-frequency signals were almost entirely absent. This was a major blow to the lightning hypothesis. On Earth, lightning produces a wide spectrum of radio waves, and the absence of the high-frequency component on Venus strongly suggests that whatever is creating the low-frequency noise is not a conventional lightning strike. It pointed toward a process that was fundamentally different from the cloud-to-cloud or cloud-to-ground discharges we are familiar with. So if it's not classic lightning, what could it be? Scientists have been pushed to propose more exotic explanations for these mysterious electromagnetic signals. One fascinating possibility is a process known as electrical breakdown, which could occur during particularly powerful volcanic eruptions. If Venus is indeed volcanically active, as the mounting evidence suggests, an eruption could blast a massive plume of ash and rocky debris high into the atmosphere. The violent collision of these ash particles within the plume could generate immense static charges, leading to spectacular discharges within the volcanic cloud itself. This would be similar to the dramatic lightning storms seen in the ash plumes of volcanoes on Earth, like Mount St. Helens or Eyjafjallajökull. On Venus, such volcanic lightning would be a localized and intermittent phenomenon, not a planet-wide weather event, which could explain why it's so difficult to detect consistently. Another compelling theory moves away from geology and into pure atmospheric chemistry. Some researchers suggest that the strange electrical signals could be caused by a type of atmospheric tide, a powerful wave traveling through the dense air that somehow generates electrical currents. Or it could be the result of a charge separation process we simply haven't discovered yet, one that operates efficiently in a supercritical carbon dioxide atmosphere laced with sulfuric acid, conditions we cannot replicate in any laboratory on Earth. The very environment that makes Venus so hostile might be fostering a unique form of electrical discharge, one that produces low-frequency radio waves without the telltale high-frequency crackle of terrestrial lightning. The question of lightning on Venus is far more than an academic debate about weather patterns. It has profound implications for the planet's chemistry and even its potential for life. Lightning is a powerful force of chemical creation. The immense energy in a bolt can break apart stable molecules in the atmosphere, allowing them to reform into new, more complex compounds. On the early Earth, lightning is thought to have played a role in creating the precursor molecules for life. If lightning does occur on Venus, even in a strange and non-terrestrial form, it would be actively altering the composition of the atmosphere, potentially contributing to the mysterious chemistry of the unknown ultraviolet absorber. The search for a definitive answer continues, a driving goal for future missions that will carry even more sensitive instruments to finally listen in and determine whether the skies of Venus crackle with a familiar fire or hum with an entirely new and unknown form of power. Rising from the global volcanic plains like a colossal, weathered continent, Ishtar Terra stands as one of the most dramatic and perplexing features in the entire solar system. This is not a simple mountain range or a large volcano. It is a vast highland plateau roughly the size of Australia, a single geological province so massive it dominates an entire hemisphere of Venus. Its very existence is a profound contradiction. On a world that supposedly lacks the plate tectonic machinery to build such grand features, Ishtar Terra is a glaring anomaly, a monument to forces we are still struggling to comprehend. At the heart of this highland fortress sits its crowning glory and deepest mystery, Maxwell Montes. This is the highest mountain on Venus, towering nearly 7 miles above the planet's mean elevation. To put that into perspective, its peak reaches higher into the sky of Venus than Mount Everest does into ours, a staggering achievement of geological force. But Maxwell is more than just tall. Its slopes are among the brightest features on the planet when viewed with radar, which sees through the thick clouds. This suggests its surface is composed of a peculiar material, perhaps a metallic mineral like pyrite, or structured in a way that makes it exceptionally radar reflective. This unusual composition only adds another layer of intrigue to an already enigmatic structure. The central puzzle of Ishtar Terra is fundamentally a question of origin. On Earth, we have a ready explanation for features of this scale, plate tectonics. The Himalayan plateau, home to Everest, was built by the colossal, slow-motion collision of the Indian and Eurasian tectonic plates, a process that crumpled the crust and pushed it skyward over tens of millions of years. But Venus shows no clear, consistent evidence for the same kind of mobile, divergent, and convergent plates that shape our own world. Its crust appears to be a single, stagnant lid. So without the engine of continental collision, what titanic force could possibly have gathered so much crustal material, squeezed it together, and thrust it upwards to such dizzying heights? Planetary geologists have developed several compelling models to solve this puzzle, each painting a picture of a world with a unique and violent geological history. One leading theory suggests that Ishtar Terra is the result of a massive mantle plume, an immense upwelling of superheated rock from deep within the planet's interior. As this enormous blob of buoyant mantle material rose, it would have pressed against the underside of the crust like a giant fist, bulging it upward to form the high plateau. The complex folding and faulting seen around its edges, particularly in the rugged tesserae terrain that borders it, could then be explained by the crust subsequently collapsing and deforming under its own immense weight around the edges of this bulge. In this scenario, Ishtar is a single, monstrous blister on the face of Venus. Another fascinating hypothesis points to a process called lithospheric delamination. This complex idea proposes that a large portion of Venus's ancient, dense lower crust and upper mantle somehow became unstable and detached from the lighter crust above it. This heavy blob would then have sunk down into the hotter mantle, a process that would have created a powerful vacuum effect above it. To fill the void, hotter mantle material would have surged upward, forcing the overlying crust to warp, thicken, and rise en masse to form the gigantic plateau. It's a dramatic and catastrophic event, a geological heart attack that could have reshaped the surface in a relatively short period. A third theory incorporates a more Venus-specific idea known as asthenospheric flow. This model suggests that large-scale currents in the planet's soft, ductile mantle layer could have acted like a conveyor belt, physically dragging the overlying crust inward from surrounding areas. Imagine scrunching a rug on a smooth floor from all sides toward the center. The rug will pile up and wrinkle. On a planetary scale, this scrunching and piling of crust could have created the concentrated highland we see today, with the intense compression generating the intense folding and faulting that characterizes its borders. Each of these theories has its merits and its complications, and the true answer may well involve elements of all three, revealing a geological history for Venus that is far more dynamic and complex than its stagnant lid surface might suggest. Ishtar Terra, therefore, is more than just a strange mountain. It is a key to unlocking the inner workings of Venus. Its formation tells a story of a planet struggling to lose its immense internal heat through mechanisms very different from Earth's plate tectonics. It suggests that while Venus may not have a fragmented and mobile crust, its interior is still fiercely active, capable of concentrating immense energy to create singular, breathtaking features through episodic and cataclysmic events. Understanding how this Australian-sized fortress was built is crucial to answering the bigger question of why Earth's twin, so similar in so many ways, chose such a different and explosive path to geological maturity. High in the Venusian sky, on the isolated peaks of mountains like Maxwell Montes, another layer of the planet's mystery unfolds, one that presents a fascinating contradiction. Radar maps of the surface reveal a startling pattern. The highest mountaintops are not just elevated, they are exceptionally bright, reflecting radar signals with a brilliance that makes them stand out like beacons against the darker volcanic plains. This phenomenon was so striking that scientists initially, and somewhat poetically, referred to it as snow. But of course, this cannot be the water ice we know on Earth. With surface temperatures hovering around 870 degrees Fahrenheit, any form of water ice would vanish in an instant. So what is this enigmatic, glittering material carpeting the highest points on this infernal world? The search for an answer forces us to think about chemistry under the most extreme conditions. The substance must be stable at searing temperatures yet volatile enough that it only condenses at the cooler, higher altitudes of the mountain peaks, much like water vapor condenses into snow on Earth's mountains. This points toward a process of metallic volcanism, a concept that sounds like science fiction, but is a serious scientific hypothesis for Venus. The leading candidates are frosts composed of heavy metal compounds that sublimate, transitioning directly from a gas to a solid, in the slightly cooler temperatures found at high elevations. Two prime suspects have emerged from laboratory experiments and atmospheric models. The first is lead sulfide, commonly known as the mineral galena. On Earth, galena is a shiny, metallic-looking ore. The second candidate is bismuth sulfide, another metallic-looking compound. Both of these minerals have sublimation points that align perfectly with the temperature range found on the Venusian highlands. The theory suggests that these metallic elements, along with others like tellurium, are vaporized by the intense heat at lower elevations, becoming a component of the dense, gaseous atmosphere. As these enriched gases rise on wind currents and sweep up the slopes of the Great Mountains, they encounter the slightly less hellish conditions of the high altitudes. There, just a few dozen degrees cooler, the vapors reach their condensation point and settle out of the atmosphere, coating the rocks in a fine, glittering metallic frost. This process would create a reverse of Earth's water cycle, a bizarre meteorological loop where mountains are capped not with frozen water, but with a condensate of vaporized metal. This snow would be utterly alien to our experience, a heavy, metallic dust that sparkles under the dim orange glow filtering through the clouds. Yet for all its compelling logic, this explanation remains unproven. No lander has ever reached these high altitudes to sample the material directly, and our orbital radar can only tell us that something is there, not precisely what it is. The mystery of the mountaintop snow is a perfect example of how Venus constantly challenges our earthly biases, presenting us with geological and chemical processes that operate by a completely different set of rules, reminding us that even our most logical conclusions must remain open to the possibility of something even stranger. Yet another layer of complexity in the Venusian atmosphere reveals itself not as a visible feature, but as a haunting chemical signature that pulses and wanes for reasons we are still striving to understand. High above the scorching surface, in the cold, thin upper reaches of the atmosphere, instruments on orbiting spacecraft have detected wild and unpredictable swings in the concentration of sulfur dioxide gas. This isn't a gentle, seasonal variation. It's a dramatic ebb and flow, with the gas's abundance sometimes plummeting by a factor of 10 over just a few Earth days before mysteriously surging back again. These drastic fluctuations present a classic scientific whodunit, forcing researchers to choose between two equally compelling explanations, one pointing to a geologically alive world, and the other to a complex atmospheric engine whose mechanics we have yet to fully decipher. The volcanic eruption theory is the most intuitively satisfying explanation. On Earth, a sudden, massive spike in atmospheric sulfur dioxide is one of the most reliable indicators that a volcano has just erupted, blasting vast quantities of the gas high into the sky. If the same is true on Venus, then these sharp increases could be our best indirect evidence of ongoing, large-scale volcanic activity. The logic is compellingly straightforward. A powerful eruption injects a fresh pulse of SO2 from the planet's interior into the upper atmosphere, creating a temporary spike. Then, over the following weeks, the intense ultraviolet radiation from the sun relentlessly breaks the molecules apart, causing the concentration to gradually fade until the next eruption replenishes the supply. This would paint a picture of a volcanically dynamic world, with occasional monstrous eruptions that punch through the thick atmosphere and temporarily alter its chemical makeup on a global scale. However, this simple volcanic narrative runs into a significant hurdle of timing and persistence. The planet-wide resurfacing event is thought to have ended hundreds of millions of years ago, and it's difficult to explain why such catastrophic eruptions would still be occurring with the frequency needed to account for the observed fluctuations. This inconsistency has led many atmospheric scientists to propose a more nuanced and perhaps even more fascinating alternative. They suggest that the variable sulfur dioxide might not be a story of injection from below, but one of mysterious circulation and chemistry from within the atmosphere itself. This second theory posits that the atmosphere of Venus might be acting like a giant, slow-moving chemical elevator. In this model, sulfur dioxide is constantly being produced at a more steady rate by smaller, background volcanic activity. The key to the puzzle is not the source, but the journey. The gas could be transported from the lower atmosphere, where it's abundant, up to the cloud tops by a massive, planetary-scale circulation pattern. Once it reaches the upper atmosphere, the solar UV radiation acts as a destructive sink, breaking it down. The fluctuations we see from orbit, then, might not be caused by individual eruptions, but by variations in the efficiency and speed of this giant atmospheric conveyor belt. Changes in the strength of the thermal tides or the super-rotating winds could alternately open and close this vertical pipeline, causing the SO2 levels at the top to soar and crash without a single new volcano needing to erupt. Unraveling which of these theories is correct is more than an academic exercise. It strikes at the very heart of understanding Venus's current state. If the volcanic explanation is true, it confirms that the planet is still geologically active in a major way, violently releasing its internal heat and potentially contributing to the mysterious chemistry of the clouds above. If the atmospheric circulation model prevails, it means we have discovered a previously unknown and incredibly powerful weather system capable of moving and processing gases on a planetary scale, a dynamic process unlike anything we see on Earth. Future missions, equipped with sensors designed to trace the precise path of these sulfur molecules, will be the ultimate arbiters in this debate, finally revealing whether the pulses of sulfur dioxide are the breath of a fiery world or the heartbeat of a complex and alien sky. Of all the planets in our solar system, Venus is the nonconformist, the one that defiantly breaks the rules, and nowhere is this more fundamental than in its very spin. While every other planet, with the minor exception of Uranus, rotates counter-clockwise on its axis as seen from above the North Pole, Venus spins clockwise. It's a backward or retrograde rotation. And as if that weren't strange enough, it does so at a glacial pace. A single day on Venus, the time it takes to complete one full rotation, lasts 243 Earth days, which is actually longer than its year. This means the Sun rises in the west and sets in the east only twice for every time the planet completes a full journey around our star. This bizarre combination of a reversed and incredibly slow spin is one of the most profound mysteries about our sister planet, and its origin story likely involves a cataclysmic event in the solar system's violent early history. The most dramatic and widely discussed theory to explain this anomaly is a colossal impact. In the solar system's formative years, a chaotic billiards game of planetary embryos and protoplanets was still underway. The leading hypothesis suggests that a young, rapidly spinning Venus, likely rotating in the same prograde direction as its siblings, was struck a glancing blow by another planetary body, perhaps the size of Mars or even larger. This wasn't a direct, head-on collision that would have shattered the planet, but a massive, side-swiping impact. The physics of such an event are staggering to contemplate. The incredible torque from this off-center smash could have literally flipped the planet over, reversing its spin entirely. Alternatively, the impact might not have flipped it but simply applied enough counter-force to its original rotation to slow it down, stop it completely, and then set it spinning backwards. In this scenario, Venus's current slow rotation is the dying echo of that ancient, world-altering crash, a fossilized record of a single moment of unimaginable violence billions of years ago. However, not all scientists are convinced that a single giant impact is the sole culprit. An alternative, more gradual theory involves the powerful gravitational influence of the Sun and the planet's own dense atmosphere. This model points to gravitational tides. Just as the Moon's gravity pulls on Earth's oceans to create the tides, the Sun's gravity exerts a tidal force on the solid body of Venus. Because Venus has no large moon of its own, the Sun is the dominant external gravitational influence. Over billions of years, this relentless tugging may have acted as a brake on the planet's initial rotation, steadily slowing its spin. But this alone doesn't easily explain the reversal from prograde to retrograde. This is where Venus's thick atmosphere enters the story. The Sun also exerts a gravitational pull on the planet's massive atmosphere, which contains most of its mass. The friction between this sluggishly moving, sun-tugged atmosphere and the planet's surface could have created a torque, a twisting force that, over eons, not only helped slow the spin but eventually overcame it and began to drive the rotation in the opposite direction. It's a theory of slow, persistent influence rather than a single catastrophic event. A battle of forces between a star, a sky, and a world that eventually resulted in the strange spin we observe today. Perhaps the most compelling aspect of this mystery is that these two theories are not necessarily mutually exclusive. It's entirely possible that both a giant impact and atmospheric tides played a role. A monumental collision in the distant past could have initially slowed Venus's rotation to a near standstill or even given it a slight retrograde nudge. Then, over the subsequent billions of years, the gravitational tides from the Sun and the torque from its own super-rotating atmosphere could have fine-tuned that spin, slowing it further to its current, agonizingly slow pace. This hybrid model acknowledges that planetary evolution is rarely the result of a single cause, but rather a complex interplay of catastrophic accidents and relentless, gradual processes. Unraveling which forces were most responsible is crucial because a planet's rotation is a primary driver of its entire character, influencing its magnetic field, its weather patterns, and ultimately, its potential for habitability. The slow, backward waltz of Venus is a silent reminder that the histories of planets are written in their motion, and our sister planet's story appears to have a uniquely violent and complex first chapter. This dramatic temperature plunge creates a bizarre situation where the atmospheric layer that is hottest by day becomes the coldest part of the entire planet by night. A thermal seesaw of incredible magnitude. This isn't a gentle cooling. It's a deep freeze that fundamentally changes how the atmosphere behaves. The thermosphere is the region where the atmosphere thins out into the vacuum of space, and it's here that the most volatile atmospheric escape processes occur. The extreme cold on the night side causes the gas molecules there to slow down dramatically, becoming denser and collapsing inward toward the planet. This creates a massive pressure differential, essentially turning the entire night side into a low-pressure sink that pulls material across the terminator from the bloated, hot day side. This cold trap acts as a powerful brake on atmospheric escape, as molecules are less energetic and less likely to achieve the velocity needed to break free from Venus's gravity. It's a complex, planet-wide balancing act where the frigid stillness of the night actively works to hold onto the atmosphere that the furious day side is constantly trying to lose. Unraveling the cause of this intense cooling is a major focus for atmospheric scientists. The leading explanation points to a process known as carbon dioxide recombination, and it hinges on a key property of the CO2 molecule. During the day, the sun's intense ultraviolet radiation bombards the thermosphere, providing immense energy that heats it and also breaking apart carbon dioxide molecules into their constituent carbon and oxygen atoms. This process requires a tremendous amount of energy which is absorbed from the sunlight. However, when night falls, the situation reverses dramatically. In the absence of solar energy, those same carbon and oxygen atoms have an opportunity to recombine back into carbon dioxide molecules. This recombination process isn't free. It actually releases a burst of energy. But crucially, this energy isn't released as heat that warms the immediate surroundings. Instead, it is radiated away directly into space as infrared light, effectively acting as a powerful planetary coolant. It's as if the atmosphere is using its own chemical bonds as a heat pump, sucking thermal energy from the night side and dumping it coldly into the void. This efficient radiative cooling mechanism is supercharged by Venus's particular atmospheric composition. The planet's air is almost pure carbon dioxide, providing an enormous reservoir of molecules perfectly suited for this cycle of breaking and reforming. Furthermore, the lack of other gases that could potentially trap this radiated heat allows the cooling to proceed with devastating efficiency. The process is so effective that it creates what scientists call a cryosphere in the upper atmosphere, a zone of intense cold that behaves completely opposite to the rest of the infernal world below it. This isn't just a curious detail. It's a dominant physical process that shapes the dynamics and evolution of the entire atmosphere, showcasing how a planet's specific chemistry can create environmental extremes that defy our simple intuitions and remind us that the physics of other worlds can operate by a dramatically different set of rules. Given the sheer scale of time involved, the possibility that Venus was not only habitable but actually inhabited is a breathtaking scientific prospect. If this world maintained stable, temperate conditions for 2 to 3 billion years, that is more than enough time for life to emerge and establish a foothold, just as it did on Earth during a similar period. This shifts our perspective of Venus from a purely hellish cautionary tale to a potential graveyard of a biosphere, a world that may have experienced its own spring before its long, fiery summer. The profound question then becomes, if life did arise in those hypothetical shallow seas, what traces might it have left, and could any evidence possibly survive the apocalyptic conditions that followed? The search for such evidence is the ultimate planetary detective story, a hunt for ghosts in a machine that has been utterly obliterated. The global resurfacing event that buried the ancient, cratered terrain under miles of fresh lava would have been the single greatest extinction event imaginable, scorching the entire planet clean. Any surface fossils or geological biomarkers would have been incinerated and buried deep beneath the volcanic rock. This makes the prospect of finding direct evidence of past life, like fossilized microbes, seem nearly impossible. However, life is tenacious, and its signatures can be surprisingly durable. Scientists speculate that our best hope may lie in the one place the lava did not reach, the ancient tesserae highlands. These uniquely deformed and incredibly old landscapes, like Terra, are believed to be the last surviving scraps of the pre-resurfacing crust. They are the closest thing Venus has to continental crust, and they may have been the last refuges, the final islands, as the oceans evaporated and the climate spiraled out of control. If life existed in those dying seas, its final chapters may have been written in the rocks of these highlands. A future mission capable of landing on this complex terrain, drilling into the rock, and analyzing its chemistry could search for indirect signs of life or biosignatures. These wouldn't be bones or shells, but subtle chemical clues. An unusual ratio of carbon isotopes, or specific organic molecules that are more likely to be produced by biological processes than by geology alone. Finding such evidence in the oldest rock on Venus would be a discovery of monumental importance, suggesting that life is not a unique miracle of Earth, but a natural, and perhaps common, outcome of planetary evolution under the right conditions. This line of inquiry leads to an even more radical and captivating possibility. That life didn't just die out, but might have retreated. The same climate models that suggest a habitable past also show that the planet's descent into inferno was not instantaneous. As the oceans slowly boiled away over millions of years, any potential life forms would have been forced to adapt or perish. This raises the extraordinary notion that Venusian life, if it existed, might have followed the water vapor upward, seeking refuge in the only environment that remained vaguely clement, the clouds. The temperate cloud deck, with its Earth-like pressure and temperature, could have become a last-chance saloon for airborne microbes. This would transform the mystery of the unknown ultraviolet absorber from a purely chemical puzzle into a potential astrobiological one. The idea that the dark, absorbing patches in the clouds could be vast, floating microbial ecosystems is the longest of long shots, but it is a hypothesis that connects the planet's habitable past directly to its enigmatic present, suggesting that the story of life on Venus may not be over, but merely suspended in a permanent aerial limbo. Beyond the vast volcanic plains and the crumpled highlands, Venus holds another unique geological signature, one that looks like a cosmic fingerprint pressed into its crust. These are the coronae, singular corona, a name taken from the Latin for crown, and they are truly fit for a planetary queen. Imagine a gigantic, circular bullseye etched into the landscape, sometimes hundreds of miles across. At its heart is a raised, dome-like plateau. Surrounding that is a moat, a depressed trench or a ring of concentric fractures, and encircling the entire structure is a raised, wrinkled rim, as if the planet's skin had been pushed up from below and then slumped back down at the edges. They are not impact craters, and they are not volcanoes, though they are often associated with volcanic activity. They are something entirely unique to Venus, a testament to the peculiar ways this world manages the heat brewing in its interior. The prevailing theory for their formation points to the action of mantle plumes, those massive upwellings of superheated rock that rise from the boundary between the planet's core and its mantle. The process is thought to begin when one of these colossal blobs of buoyant material ascends through the mantle and presses firmly against the underside of Venus's rigid outer shell, the lithosphere. The immense heat and pressure from below cause the crust above to blister upward, creating the broad, domed center characteristic of a corona. This uplift stretches and fractures the rock, creating the web of cracks and faults that typically pattern the corona's interior. But the story doesn't end with the uplift. Eventually, the mantle plume begins to cool and lose its energy. It dissipates, or perhaps it moves on, like a subterranean storm passing over the landscape. As the supporting force from below weakens, the heavy dome of rock, now unsupported, begins to collapse back under its own immense weight. The center sags, forming the distinctive trough or moat. Meanwhile, the material that was pushed outward during the initial uplift continues to slump downward, piling up at the edges and creating the prominent raised rim that gives the corona its crowned appearance. This entire cycle, upwelling, stretching, and collapse, creates a complex geological record of rise and fall frozen in time. However, this seemingly straightforward model is complicated by the stunning diversity of coronae we see. Some are almost perfectly circular, while others are elliptical or even irregularly shaped. Some have incredibly prominent rims and deep moats, suggesting a violent collapse, while others appear much more subdued, as if the uplift was gentle and the settling was peaceful. This variety suggests that the simple blob and collapse model might be too simplistic. The exact interaction between the mantle plume and the Venusian lithosphere, which behaves differently from Earth's due to the extreme surface heat and pressure, is incredibly complex and not fully understood. The thickness and strength of the crust at the time of the plume's arrival, the persistence and temperature of the plume itself, and even the influence of pre-existing tectonic features all likely play a role in determining the final form of a corona. Some scientists propose that certain coronae, particularly those with extensive volcanic flows around them, might represent an intermediate stage between a purely plume-driven uplift and a full-blown volcanic eruption, a place where the planet's internal heat almost, but not quite, breaks through to the surface in a catastrophic outpouring of lava. Unraveling the precise mechanics behind each type of corona is like reading a different chapter in the story of how Venus releases its internal heat. A story that is written in rings of fractured rock across the face of our mysterious sister planet. While the lower atmosphere of Venus is a suffocating blanket of carbon dioxide, the upper layers hold a far more ethereal and puzzling secret. High above the scorching surface, where the atmosphere thins out into the void of space, orbiting spacecraft have made a detection that seems completely out of place, a distinct layer of atomic oxygen. This finding is as unexpected as finding a snowflake in a furnace, and it presents a fascinating chemical puzzle that challenges our understanding of how the Venusian atmosphere interacts with the fierce radiation from the sun. This oxygen isn't the breathable O2 that sustains life on Earth. It's something more fundamental. It's a layer of single oxygen atoms, a highly reactive and ephemeral form of the element that shouldn't persist for long. On Earth, we have a permanent layer of ozone, a molecule made of 3 oxygen atoms that protects us from ultraviolet light. Venus has no such shield. Its atmosphere is constantly bombarded by the sun's full intensity, which ruthlessly breaks molecules apart. So the very existence of this concentrated band of atomic oxygen suggests there is a continuous and efficient production process at work, one that is constantly replenishing this layer against the relentless forces of destruction. The leading theory for its creation points directly to the action of sunlight itself. The process begins with the workhorse of the Venusian atmosphere, carbon dioxide. The sun's powerful ultraviolet radiation slams into CO2 molecules high in the atmosphere, providing enough energy to violently break their chemical bonds. This photodissociation, or splitting by light, shatters the carbon dioxide into its constituent parts, a carbon monoxide molecule and a single atom of oxygen. This is happening on a colossal, planet-wide scale. But this alone doesn't create a stable layer. It just creates a chaotic soup of ingredients. The mystery is how these individual atoms are then gathered and organized into the distinct, concentrated band that spacecraft have detected. This is where the complex dynamics of the Venusian atmosphere come into play. Scientists believe that atmospheric winds and circulation patterns act like a giant, invisible loom, weaving these individual threads of oxygen into a coherent tapestry. The super-rotating winds and the giant Hadley circulation sells large-scale patterns of rising and falling air, are thought to transport these freshly created oxygen atoms, concentrating them at a very specific altitude where conditions are just right for them to accumulate. It's a delicate balancing act between creation by sunlight, transportation by wind, and destruction through recombination with other elements. The persistence of this layer means these forces have reached a temporary equilibrium, a testament to the dynamic and continuous chemical factory that is Venus's upper atmosphere. However, seamlessly integrating this discovery into our planetary models has proven difficult. The detected density and distribution of the atomic oxygen don't always perfectly match what our theoretical simulations predict. This discrepancy is a classic sign that we are still missing a piece of the puzzle. It suggests that there might be other, more subtle processes at work that we haven't yet accounted for. Perhaps there is an additional, unknown source of oxygen, or maybe our understanding of the wind patterns at that precise altitude is incomplete. It could be that the rate at which oxygen atoms recombine with other molecules to form carbon dioxide again is different than we calculated under those extreme conditions. Each of these possibilities points to a gap in our knowledge of fundamental atmospheric physics. The significance of this oxygen layer extends far beyond a simple chemical anomaly. It acts as a crucial regulator in the planet's energy budget. When these oxygen atoms eventually do collide and recombine with carbon monoxide to form carbon dioxide again, the process releases heat. This energy is then radiated out, directly influencing the temperature and structure of the upper atmosphere, which in turn affects how the atmosphere evolves over time. Furthermore, this constant cycle of breaking and making CO2 is a primary mechanism for the slow but steady escape of other elements into space. Understanding the precise mechanics of this oxygen layer is therefore essential for piecing together the entire history of the Venusian atmosphere, how it became so dense, how it lost its water, and how it continues to change even today. It is a subtle clue, a faint chemical signature written in the thin, cold air high above the hellscape, that holds the key to the planet's past and future. Long before our modern probes pierced its clouds, astronomers peering through Earth-bound telescopes were charting the subtle, shifting patterns in the veil of Venus, and in the early 20th century, they recorded a truly bizarre and singular event. In 1927, an esteemed French astronomer named Michel Baltz was conducting a routine observation when he witnessed something that defied all explanation. A large, distinct, and intensely dark spot moving across the planet's brilliant disk. This wasn't a faint smudge or a questionable blur. His detailed notes describe it as a well-defined black patch, an in-sky void against the bright clouds, and he carefully tracked its progression as it appeared to drift slowly across the face of Venus over several days of observation. He dubbed it the Black Lady, a poetic name for a profoundly mysterious phenomenon. The spot was massive, potentially thousands of miles across, and its movement suggested it was part of the atmosphere. Yet its profound darkness and sharp definition were unlike any other transient feature ever recorded before or since. This historical anomaly presents a multi-layered puzzle for modern planetary scientists. The first and most critical question is one of authenticity. Did Michel Baltz truly see what he described? He was a respected observer, and there is no reason to doubt his honesty or his eyesight. But the human element and the limitations of early 20th century optics always introduce a degree of uncertainty. Could it have been an optical illusion, a temporary flaw in his telescope's lens, or even a spot on his own eye? While possible, the fact that he was able to track its consistent movement over multiple observing sessions makes these simple explanations feel less likely. He wasn't just glancing, he was methodically documenting a persistent feature. This pushes us to consider that he might have witnessed a real, albeit monstrously rare, atmospheric event on Venus, a transient phenomenon of such scale and intensity that it has not been repeated in the century of superior observation that has followed. If we accept that the Black Lady was real, the next challenge is to identify what kind of atmospheric event could possibly create such a feature. The description of a large, well-defined, and very dark spot doesn't neatly align with any of the phenomena we now understand to occur in the Venusian atmosphere. Our modern probes have shown us the planet's subtle, streaky cloud patterns and the giant Y-shaped wave, but nothing with the stark, localized contrast that Baltz reported. One compelling theory suggests he may have witnessed the consequences of a cataclysmic volcanic eruption, far larger than any in recorded human history. Imagine a volcano so powerful that it punched a temporary hole right through the upper and middle cloud decks, venting a massive plume of dark, ash-filled gas from the lower atmosphere into the stratosphere. This could theoretically create a temporary void, a window of sorts, through which the telescope was essentially looking down into the deeper, darker layers of the atmosphere, creating the impression of a moving black spot. Another, more exotic possibility involves a colossal atmospheric upheaval. The super-rotating atmosphere is a system of immense energy, and it's conceivable that it could occasionally spawn a monster storm, a hurricane-like vortex of such intensity that it churned up deep, dark material from the lower atmosphere, concentrating it into a single, coherent dark mass that swirled within the brighter clouds for a brief period. This would be akin to a gigantic version of the Great Dark Spot on Neptune, a massive atmospheric eddy that pulls up material from the deeper layers. A third, even more speculative idea points to the mysterious ultraviolet absorber. Could some unknown process have caused this unknown substance to concentrate suddenly and violently in one region of the atmosphere, creating a temporary, super-dense patch that appeared as an exceptionally dark feature to Baltz's eye? Each of these explanations is a stretch, requiring a perfect and unlikely storm of atmospheric conditions, which is perhaps why such an event has never been seen again. The enduring mystery of the Black Lady is that it exists as a solitary data point, an uncorroborated glimpse of something extraordinary in the historical record. No other astronomer from that era independently confirmed the sighting, and no subsequent observation by any telescope or spacecraft has ever recorded anything remotely similar. It stands alone, a ghost in the early logs of planetary science. This doesn't diminish its intrigue. Instead, it elevates it to the status of a legendary celestial event. It serves as a powerful reminder that even with all our advanced technology, we have only been studying the planets in detail for a blink of an eye in their long histories. Venus may be capable of paroxysms of activity, of unleashing colossal events that operate on timescales of centuries or millennia, events that we have not been watching long enough to catch. The Black Lady remains a tantalizing whisper from the past, a hint that our sister planet may still hold secrets of a scale and ferocity we have yet to imagine. This peculiar absence of small craters presents a fascinating forensic puzzle, one that reveals as much about the planet's atmosphere as it does about its surface. When planetary scientists first mapped Venus using radar, they expected to find a distribution of impact craters similar to other rocky worlds, a mix of large, medium, and small, with the smaller ones being far more numerous, just as we see on the Moon or Mercury. Instead, they discovered a landscape that seems to have been meticulously curated. The smallest craters, those less than a few kilometers in diameter, are almost entirely missing. It's as if a cosmic sieve has been placed over the planet, filtering out all but the largest incoming projectiles. And the prime suspect for this filter is Venus's incredibly dense atmosphere. The logic behind this atmospheric filtering is both simple and awe-inspiring. A meteoroid hurtling toward Venus first encounters the upper fringes of its atmosphere. a medium far thicker and more substantial than the near vacuum that greets incoming objects at Earth or Mars. This isn't a gentle breeze, it's like slamming into a wall of fluid. As the space rock plows deeper, the immense pressure and friction generate temperatures so extreme that the object begins to violently ablate. It heats up, fragments, and essentially vaporizes. For smaller meteoroids, this process is utterly catastrophic. A rock that might create an impressive 100-meter-wide crater on the Moon is completely consumed, burned away to nothingness long before it ever gets close to the Venusian surface. It's consumed in a brilliant, silent fireball high in the acidic clouds, its potential impact erased before it can even begin. The precise mechanics of this filtering, however, are a complex and nuanced area of active research. It's not just about size. The composition, speed, and entry angle of the incoming object all play critical roles. A fragile, icy comet fragment will disintegrate much more easily than a sturdy, iron-nickel asteroid of the same mass. An object arriving at a shallow, grazing angle will spend much more time traversing the atmosphere, subjecting it to far greater stress and heat than one striking head-on. Scientists use sophisticated computer models to simulate this violent atmospheric entry, trying to pinpoint the exact threshold where an object's size and strength allow it to punch through versus when it's utterly annihilated. Understanding this threshold is crucial because it allows us to use the crater record as a calibrated tool. By noting the smallest crater sizes that have managed to survive, we can actually work backwards to calculate the density and protective power of the atmosphere at the time those impacts occurred. This turns the crater record into a kind of historical archive. The current scarcity of small craters tells us that Venus's atmosphere has been incredibly thick for at least the last several 100 million years, essentially throughout the period recorded by its existing surface. But if we could find and date a handful of exceptionally small, exceptionally well-preserved craters, it could provide a vital clue. Their presence would suggest that at the moment of that impact, the atmosphere might have been slightly thinner, perhaps during a brief, anomalous period in its climatic history. The near-total absence of these small features is therefore a powerful piece of evidence supporting the idea of a long-standing, stable, and intensely hostile atmosphere. A permanent barrier that has shielded the surface from all but the most determined celestial bombardments for a vast stretch of geological time. And so we arrive at our final and perhaps most human mystery, one that speaks not just to the alien nature of Venus, but to the triumph and heartbreaking fragility of our own attempts to touch it. In the 1970s and 80s, the Soviet Union embarked on one of the most daring campaigns in the history of space exploration, landing a functioning spacecraft on the surface of Venus. The challenges were beyond monumental. They were considered nearly insurmountable. Engineers had to design a probe that could withstand an atmospheric pressure equivalent to being 3,000 feet underwater on Earth, temperatures hot enough to melt lead and zinc, and clouds of corrosive sulfuric acid. The accepted wisdom was that any lander would be crushed, melted, and dissolved within minutes. The Venera probes were designed with this brutal calculus in mind, built to survive for a mere 30 minutes on the surface, just long to snap a few grainy photographs, take some basic readings, and scream its data back to Earth before succumbing to the inevitable. But then, something extraordinary happened. Several of these brave little landers didn't die on schedule. Venera 13, the champion of them all, kept talking. It continued to transmit data for 127 minutes, more than double its planned lifespan. This wasn't a minor overrun. It was a staggering feat of endurance that fundamentally changed our understanding of the Venusian surface environment and left engineers and planetary scientists scratching their heads for decades. What unknown factor, what hidden property of that hellscape, or what incredible feature of its own rugged construction allowed it to cling to life for so long against all odds? The answer is a fascinating detective story of engineering forensics and environmental guesswork. One of the most compelling theories points not to a failure of the environment, but to a surprising and unforeseen success of the lander's own design. The Venera landers were, by necessity, hermetically sealed pressure vessels, essentially giant, sophisticated thermos bottles designed to keep their delicate internal electronics cool for as long as physically possible. They were packed with advanced insulation and even contained a pre-chilled cooling system to give them a fighting chance. It's possible that the combination of this impeccable insulation and the specific way the lander came to rest on the surface created a perfect, if temporary, thermal equilibrium. Perhaps it settled into a small depression or on a patch of soil that provided a minuscule amount of additional insulation from the searing heat radiating from the surrounding rocks. The lander's own systems, fighting a desperate rearguard action against the heat, might have simply been more efficient than anyone had dared to hope, slowly and heroically warding off the inevitable for just a little while longer. Another hypothesis ventures outside the lander and into the strange environment itself. Some planetary scientists have suggested that the Venusian surface might occasionally experience a phenomenon that is almost unthinkable given the overall conditions: a gentle breeze. The atmosphere at the surface is so incredibly dense that it behaves more like a fluid than a gas. While the overall wind speeds are minimal, the movement of this supercritical fluid could have a profound cooling effect on any object it passes over, much like blowing on a hot spoonful of soup. If a fortuitous, slight breeze happened to play across the lander's surface, it could have carried away just enough waste heat from the metal hull to keep the internal temperature below the critical failure point for a precious additional hour. This would mean that Venera 13's longevity was due to a fleeting moment of mercy from the very atmosphere that was trying to destroy it, a whisper of wind on a world of fire. The most intriguing possibility of all, however, involves the lander's interaction with the surface itself. The Venera landers were equipped to analyze the soil, and their findings suggested the material at the landing sites was not loose, dry dust, but something with a more cohesive, almost clay-like consistency. This has led to a fascinating idea. Did the lander sink? If the leg pads settled into a thin, cooler layer of soil, it could have effectively buried the lower, hotter part of the probe's body in a rudimentary insulating blanket. This subsurface material, shielded from the direct radiant heat of the surface and the atmosphere, might have been significantly cooler than the air temperature just inches above it. In this scenario, the very ground of Venus, often portrayed as a plane of fire, may have offered a temporary haven, cradling the lander and slowing its internal cook-off in a way the designers never could have predicted. We will likely never know the exact combination of factors that granted Venera 13 its bonus hour of life. The final moments of that transmission are the stuff of silent tragedy, a gradual slowing of data, a sensor failing, then another, until finally, the signal ceased forever. It had gone dark, not with a bang, but with a fading whisper. Yet its stubborn refusal to die quickly became a legendary chapter in the story of space exploration. It taught us that Venus, for all its fury, might have pockets of slight moderation, tiny nuances in its hellishness that can be exploited. It proved that human ingenuity could create a machine so tough it could defy expectations on another world. And most of all, it left us with a final, poignant mystery, a testament to the fact that even in the most hostile environments, the will to learn, to explore, and to endure can sometimes, against all logic, win a few more precious minutes. From its potential as a lost oasis to its present-day inferno, Venus presents a tapestry of mysteries so profound they redefine our understanding of planetary science. We have journeyed through 25 of its greatest enigmas, from the driving engine behind its super-rotating atmosphere and the haunting case of its missing water, to the bizarre metallic snow on its mountain tops, and the fleeting, historical glimpse of the enigmatic Black Lady. We've pondered the possibility of volcanic activity reshaping its surface, the chemical puzzle of phosphine in its clouds, and the silent, inexplicable absence of a magnetic field from a molten core. Each mystery is a thread in a larger narrative, a story of a world that started as Earth's twin but became a warning, a puzzle, and a beacon for exploration. These are not just academic curiosities. They are fundamental questions about how planets live, die, and potentially even harbor life in the most unexpected places. The enduring allure of these puzzles is precisely what fuels the next great era of space exploration. Every unanswered question is a direct mandate for a new mission, a new instrument, and a new generation of scientists and engineers. The unresolved debate over Venus's volcanic activity drives the need for orbiters with advanced radar that can map minute surface changes over time. The mystery of the ultraviolet absorber and the phosphine controversy demand probes that can dive into the cloud layers, sampling their chemistry directly. The bizarre surface features like the tesserae and coronae call for long-lived landers or even agile rovers capable of traversing that hellish landscape to analyze the planet's ancient rocks. This cycle of mystery and mission is the very heartbeat of discovery, proving that we are driven not just by what we know, but overwhelmingly by what we do not. This is why Venus is now at the forefront of planetary science, with multiple agencies preparing to unveil its secrets. NASA Defies mission will send a descent probe through the atmosphere, sniffing its gases and snapping high-resolution images of the tesserae highlands. The Veritas orbiter will map the surface in exquisite detail, searching for hints of active geology and mapping its gravitational field to understand its interior. The European Space Agency's Envision orbiter will complement these efforts with its own suite of powerful instruments. Together, these missions represent a collective global effort to turn these 25 mysteries into 25 breakthroughs, transforming the unknown into the known and undoubtedly revealing new questions we cannot yet even conceive. As we stand on the precipice of these new discoveries, the conversation continues with all of you. Which of these Venusian mysteries captures your imagination the most? Does the thought of a potential aerial biosphere floating in the temperate cloud decks fill you with wonder? Are you captivated by the geological forces that built the Australian-sized highland of Ishtar? Or does the simple, profound tragedy of a runaway greenhouse effect that transformed a potential paradise into a purgatory serve as the most compelling narrative? Share your thoughts in the comments below. Let us know which puzzle you would solve first if you had the chance. The journey to understand our mysterious sister planet is one we undertake together, fueled by curiosity and a shared desire to see what lies behind the veil of those brilliant